My assumption is that this is where we left off on Monday. Yes, looks familiar. Good. Okay, so we finished the first example of a significance test, start to finish, all the way through. We're going to do a second one today together. All right, so example 2. A potato chip producer and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer finds convincing evidence that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make potato chips. The potato chip producer has just received a truckload of potatoes from the supplier. A supervisor selects a random sample of 500 potatoes from the truck. An inspection reveals that 47 of the potatoes have blemishes. Is there convincing evidence at the 0.1 level that more than 8% of the potatoes in the shipment have blemishes? So, first question is, what is the question asking me to do? Take a minute, turn to your neighbors. What is the question asking us to do, and how do you know? All right, do I have a volunteer? Yes, I'll stop. Okay, and how do you know it's a significance test? Very good. So they used both of those things we know are key phrases for significance tests. Is there convincing evidence? They gave us a significance level. Those two things together are definitely 100% I am doing a significance test. Very good. Now that I know that I am doing a significance test, the next question is, what am I doing a significance test for? What is the population parameter of interest? Potatoes with blemishes, and they gave us a percentage. Percentage means what? What are we doing claims about in this unit? Proportions. If it's a statement about a percentage, this is a proportion test. So we are doing a 1 proportion z test. Stating what I'm doing. And since I am doing a test for a proportion, I should define that population proportion of interest in words. And somebody already told me that it was potatoes with blemishes. So this is the proportion of potatoes on the truck with blemishes. It's important to mention truck here because the entire truck of potatoes is the population of interest. We then draw a sample from that single truckload. So far, so good. Yeah. We know in the state step, after we've defined our variable interest, we're just identifying all of the information we're given in the problem and stating our hypotheses, the claims we're going to test. So who can give me a number in the problem that I need to write down here? Marilyn. 500. Very good. So 500 random sample, that must be my sample size. Excellent. So sample size n equals 500 potatoes. Good. Excellent. Somebody other than Marilyn, another number from the problem. 47. What does 47 represent? Number of successes. Very good. You just got to speak louder with confidence. Very good. 47 blemished potatoes. Potatoes. Yes, potatoes. There is one more number they gave us that is important for a significance test, which is, very good, the 0.10, our level of significance, or significance level. Perfect. I know here I need to state my hypotheses. What are the claims I am comparing with this test? There is one more thing I should do here, not required but helpful. I know that when I get to the do step, I have to calculate a test statistic, and the test statistic depends on p hat, because it's looking where is my p hat relative to p. So I need to calculate p hat. I was not given p hat. So, very good. P hat is x over n, which we know is 47 out of 500, 0.094. Perfect, thank you. That sounds vaguely familiar. Very good. And then the hypotheses. So hypotheses should involve the population parameter of interest. We're using a P. Hypotheses should use the claimed population value from the word problem. What is the proportion of blemished potatoes that we're claiming in the problem? 8%. Very good. So 0.08, 0.08, and then I need relational symbols to go between those two things. Starting with the null, what goes between the P and the 0.08? Equals, always equals. Very good. It's always a statement of equality. Alternative comes from the word problem. Greater than. Very good. How do we know? Very good. More than 8%. We're testing a claim about whether there is more than 8% blemishes. Because if there's more than 8% blemishes, we send the truck away. Good. Perfect. Snaps. All right. Questions on the state step before we move on? No. All right. Margarita, in the plan stage, we check 3 things. Can you tell me one of the 3 things we have to check? Independence. Very good. So we have 1, 2, 3, independence. I know how to spell. Bonus point for Margarita. Do you remember how we check for independence? %, gold star. Very good. 10% condition. I'm checking my sample size versus the population size. So sample size was 500 potatoes. Should be less than or equal to 10% of, and then my population in words. What is my population of interest? All potatoes. All potatoes where? On the truck. Very good. On that shipment. On truck, in truck. I don't know how you want to say that. Very good. In that single truckload that we're looking at. Perfect. Janan, 2 more things we need to check. Can you give me one of them? Random. Very good. And I heard somebody else mumble random sample. So in the word problem, were we told this was a random sample? And the answer is yes. So you can copy the wording from the problem or state we are told they used a random sample. Make it easier to read there. One more. Gabe P. What is the last thing I need to check? Normal. Very good. Do you remember how we check for normality? Very good. So large counts. We're looking at number of successes, number of failures, making sure they're both bigger than or equal to 10. Good. So number of successes, number of failures. Number of successes we wrote down that was 47 in the plan stage. We know that, or state stage, that is definitely bigger than or equal to 10. Jala speaking. Yep, I'll send him down. Perfect. Bye. Well, that's for you. There is not any hollow pass in the system. Gibbers. Okay, so if 47 potatoes in that sample are blemished, how many are not blemished? Very good, 453, because I know those two numbers have to add up to my sample size. That is much bigger than 10. I am a happy statistician. Perfect. So remember, we're checking these. This makes sure that my sampling distribution of p-hats is normal. That's how I can use the normal distribution to make a decision about my claims. Independence checks that I can use that formula for my standard error, square root of PQ over N. Random makes sure that the center of my distribution should be the population value. So we are checking center, spread, and shape. Center, spread, and shape. Center, spread, and shape. Good. All right, after the plan stage, we are ready to do the thing. Do the thing. The question is, what are we doing? I should be calculating two things here. Test statistic, which is a z-score. I'll even put a little t down there to remind us it's the test statistic. What else will I need? A p-value that comes from that test statistic. Good. Very good. Surefire way to get a 4, you got to write the formula and then show the substitution. So on the equation sheet on test day, it's going to say statistic, sample statistic. So what is the sample statistic of interest? What are we looking at in this problem? What about the potatoes? We're looking at the proportion that are blemished. What is the sample proportion symbol that should go here? P hat. Yeah, sample proportion is P hat minus population proportion is P. Yeah, because they're not going to tell you P hat and P. They're going to say statistic and parameter, because this formula has the same structure for every test we're going to do. It won't always be a P there. Denominator is going to say standard error. So you need to go to the back page and look it up, or if you remember, PQ over N. I don't expect that you remember that. I remember it because I've been doing this for a very long time. I teach stats multiple times a year. Yay. And ideally, if we did the state step and we were nice and thorough about it, we should have all of those numbers. So this stage really is just substitution. So our sample proportion was 0.094. Population value in our alternative and null hypothesis was 0.08. In the denominator, I remember that I am using population values. 0.08. What is the complement to 0.8? Pretty sure it's 9.2. Should add to 100. Sample size is 500 potatoes. And we could plug that in our calculators. We wrote it on the page, but my assumption is none of you want to do that. So which calculator function? Well, you could do normal CDF, but normal CDF won't give you your test statistic. And I'll give you a hint. It's the name of the method we wrote down in plan. 1 prop Z test. 1 prop Z test. I'm going to scoochie it up and write it in red to remind us. Where do we find 1 prop Z test? Stat test, very good. It's going to ask us for null hypothesis, number of successes, sample size, alternative hypothesis. If you do not use the equation method that I wrote in black up in the box, and you're only using calculator speak, what should I write here instead of those symbols? The actual words: population proportion, number of successes, sample size, alternative hypothesis. If you are not writing out the equation, if you're writing out the calculator function, you have to write your inputs in words. Good. We have those values. This was a greater than claim. I'm going to give you just a minute to run that on your calculator. Scooching up a little bit. Does somebody have an answer? Maria has an answer. She's showing it to other people. 1.15 and 0.124. Do we agree with Maria? Yes. Good. Perfect. Perfect. Technically, that's enough. But if you really want to go for that 4 out of 4 on your FRQs, and you should be aiming for that, what else goes in that box? Normal curve. Very good. If you're doing inference, there should be a distribution somewhere on that paper. Ooh, but not that button. Try that again, Mr. J. Normal curve. We are looking at standard normal. This is Z's. 0 in the middle. 3 standard deviations out in either direction. And once the picture is drawn, what do we mark in the picture? P-value, and in order to mark the p-value, I first have to mark the ZT, yeah, the test statistic. Because the test statistic is the boundary value between the p-value and the not shaded. Good. So my p-value is positive 1.15, which is right about here. And in order to shade the correct part that represents my p-value one of two things. One, common sense. I know the whole curve is 100%. Which side, left or right, accurately represents about 12%? The answer is the right side, because that's the smaller side. The other way is we know we look at the alternative hypothesis, shade in the direction of the arrow. Ours was a greater than, points to the right. So I'm shading this way. And that should represent that 12.4%. What that means is assuming that 8% of the truckload is actually blemished, there is a 12.4% chance that a random sample of 500 potatoes is going to have a sample proportion greater than 8%. Is that common or uncommon? And the answer is that's not uncommon enough that I am concerned. I'm inside 2 standard deviations, and my alpha is what? 0.1. Yeah, so when I go to compare my p-val to my alpha, 0.124 is greater than 0.1. When the p-value is low, reject HO. Our p-value is not low. We should not reject the null. We do not have enough evidence with this sample of 500 potatoes to make a statement that the percentage of blemishes in that truck is more than 8%. Because it is totally reasonable to get a percentage of blemishes of like 9% from a sample of 500, even if the overall truck is 8%. That is within normal sampling variation. The question is, how do I explain that idea to the AP readers? The answer is we have 2 sentence frames. 2 sentence frames. The first one addresses the null. Because our p-value of 0.124 is greater than our alpha. We fail to reject the null. I know how to spell. Or we fail to reject HO is also fine. We do not have enough evidence to reject the claim that the population percentage is 8%, which means I also do not have enough evidence to support that the percentage is greater than 8%. So our second sentence, we're addressing the alternative. If I did not reject the null, I do not have evidence for the alternative. We do not have convincing evidence that, how do I complete that sentence? I don't have convincing evidence of what? What was our alternative claim in words? Who can tell me? More than 8%. I heard it from multiple places. I heard you, Marissa. Yeah, that more, not Mar, come on, Mr. J. More than 8% of potatoes on the truck have blemishes. While you are jotting down some reminders, once you know you're working with a proportion, we know that the plan stage should look exactly like proportions for, or statements for, confidence intervals. Because as long as it's a proportion, I'm checking those same three things: random, independent, normal with large counts. Yeah. I know that for the conclude, I have sentence frames to help me. If I have those sentence frames up here, that conclude step one will go faster. And two, those sentence frames are written in such a way that they are intended to get you full credit on the FRQ, meaning I know what the AP board is looking for when they're reading your writing. Those sentence frames are built in such a way that if you fill them out correctly, you should get that full point. Yeah? Good. On your homework, for those of you who haven't started 6D yet, not all of the questions are going to ask you to do the full state plan do conclude. I think it's only the last one or two. So if you look at the homework, it's only the ones that say, hey, here's the full significance test, where you need to do all 4 steps. Some of them are only asking you to do pieces. I think the first couple questions are just asking you to go through those 3 checks: random, independent, normal. So make sure you're reading the directions so you're not doing more work than you need to. Yeah. Before we move on to our last chunk, does anybody have questions on that example? Are we feeling a little bit better than we were on Monday about significance tests? I see some nodding. Good. Good. And we're going to get more practice. So this is not it for significance tests. Good. We have one more thing we need to talk about: the concept of errors and power in a test. And we're going to kick off this section with an analogy. So we are going to pretend that we are jurors in a jury trial. Yes, yay. And we know that in a jury trial, the jury can make decisions about whether they're guilty or not guilty. And then there is the reality of the situation, whether the person is actually guilty or not guilty. And in an ideal world, those things line up, but we know that they don't always. So in that table of our decision versus what is true in reality, where are the 2 boxes where we are happy as conscientious jurors? Where am I happy? Guilty, guilty, and not guilty, not guilty. Good. These are correct decisions. So as a juror, I have a clear conscience. I am a happy human being. I have made the correct decision. My decision matches up with the reality of the situation. The question is, what happens when reality and my decision as a juror don't agree? We'll start with this box in the upper left. What happens when I vote guilty, but the person on trial is actually not guilty? What happens? Yeah, definitely frowny face. And why am I frowny face? Just send an innocent person to jail, yeah. Frowny face. Yeah, no, we don't want to do that. In the other box, the lower right, I acquit the person. In reality, they're actually guilty. What happens? Criminal goes free, yeah. So the question is, which one of those errors that I could make as a juror is worse? Which one of those is worse? So I want you to take about 90 seconds in your group and discuss which one of those is worse and why. I'll give you about 90 seconds. That is a good point, which we will talk about in a minute.
Oh my god, the whole life.
If at any point you need to like go to the restroom or take a break, let me know. You guys are quiet. We already discussed.
My password. Melanie takes pictures.
All right, let's take a vote. We're gonna go around the class. Amanda Pendo, which one did you vote for as worse? So we have a vote for that being worse. Back table, Flor, what did your table vote for? Innocent person going to jail is worse. Miguel, what did your table vote for? Innocent person to jail. Will, what did your table vote for? Criminal goes free. Marilyn, what did your table vote for? Innocent person. Very good. Hilani, what did your table vote for? Innocent person. Very good. Isaac, what did your table vote for? Criminal goes free. Aaliyah, what did your table vote for? Earth to Aaliyah. Criminal goes free. So 50-50. Interesting, 50-50. And I have a question for you that may cause you to reconsider your answer. Would your answer change if I was talking about petty theft versus murder? And I see a lot of people nodding yes, some people shaking their head no, and that probably depends on which box you were in the first place, yeah? So if the person committed petty theft, they walked into Target and they stole some deodorant, I, at least as an adult who lives in society, right, I would much rather be here than here. Because petty theft is not something I'm really worried about that person living next door to me. They stole deodorant from a Target. Like, come on. I'm not worried about them breaking into my bedroom and murdering me at night. I would much rather err on this side rather than that side. Because I don't want somebody who didn't do petty theft to sit in jail for something they didn't do. And petty theft isn't really a huge danger to society. Yeah? Reasonable? If we're talking about somebody who is a serial murderer, which box do I want to be in? Ideally, neither, but the worst one is probably that one, right? This would be more favorable because I don't want to let a serial murderer run around my neighborhood murdering people in their sleep. So, as a statistician, we are in a similar conundrum. Which box we sit in depends on the situation. It's not always going to look the same for every test we do. It's not going to look the same for every jury trial we do. In a perfect world, we'd always be in those happy face boxes. But sadly, humans are fallible. We do not live in a perfect world. So as statisticians, we have to make a decision about which one of these error boxes is worse for the test that we are performing. All right, so let's complete the analogy and look at how the moving pieces of a jury trial match up to what we do in a significance test. So, in a jury trial, you make a decision about whether the defendant is guilty or innocent. Which part of our significance test lines up with that? Emphasis on the word decide. Where do we make a decision? We seem to be on the struggle bus. So. Reject or not reject the null. That's where we're making a decision as a statistician at the end of our test. Is after we've looked at all the evidence, do we reject or not reject the null? Never accept. Never the word accept, never the word correct, never the word true when it comes to testing. Dangerous words. We only use the phrases reject and not reject for the null. Second, in an ideal jury trial, in a perfect world, we would always start with the assumption that the defendant is innocent until proven guilty. What is the equivalent of that for our hypothesis test? What are we assuming to be true when we start? And this is tricky. We assume the null is true. How are we doing that? Our entire sampling distribution is built with that claimed population value as its center, and we see it in the formula for our test statistic. If I look at the formula for my test statistic, p hat minus p over square root pq over n, I am assuming that the population value is true, and I am using that as the center of my sampling distribution, and then measuring how far my sample is from that population value. So we are assuming the claimed value is true. Last question. Court presents evidence and a decision is made. What are we using as evidence? Better question, how do we make our decisions? What's the dividing line there? P-value, yeah, good. We use the p-value, we compare it to our level of significance, we make a decision. Good. That p-value, the probability that I get a sample as extreme or more extreme than the one that I selected, that is my evidence used to make a decision. Good. Good. So we have to deal with this enough when we're setting up significance tests that we give names to those unhappy face boxes in the table above. So let's fill out this box for a significance test instead of a jury trial. So in a significance test, I can reject the null, or I can fail to reject the null. Those are the decisions I can make. I compare p-value to alpha. If p-value is low, I reject HO. If it's not low, I fail to reject HO. The truth is that the null can be correct or the null is incorrect. And the question, and this is the same as the question for the jury trial, where are the two boxes where I am a happy statistician? Fail to reject and is correct, because I don't want to reject something that's correct. So fail to reject when it's correct is the correct decision. I don't want to reject something that is true in reality. Where's the other box where I'm happy? Very good. Reject and not correct, because I should reject something that is not correct. Good. Those boxes I'm happy. The other boxes get names. The first box, we reject the null when we should not, is called a type 1 error. Notice the use of Roman numerals. Yes, we label errors for hypothesis tests with Roman numerals. Don't ask me why I did not make that decision. Any guesses, based on what you know about statisticians, what we call that empty box? Type 2 error, very good. Or type II error if you're being silly. Yes. We have type 1 errors, type 2 errors. Type 1 error, I rejected when I shouldn't. Type 2 error, I failed to reject when I should. One of the things that the AP test is going to ask you to do in the FRQs is they will give you a scenario with the hypotheses already written out, and they'll ask you to describe what those two errors look like in terms of the scenario, in terms of the context, and then ask you about real-world consequences. We're going to practice the first half now, and we'll do the second half later. And yes, this is a silly example. Try to keep the giggles to a minimum. Suppose you are visiting a doctor's office for a pregnancy test. Below are the possible outcomes for the test. You are not pregnant. That is our null. That is what the doctor is assuming until the test comes back positive. Or the test comes back positive, you are pregnant. Yeah. And we are again assuming when you visit the doctor, the assumption is not pregnant until the test shows otherwise. So we're going to use that information to fill out the table on the next page. So, there you go. Ooh, yeah, I'm hearing good words. That makes me happy. So let's fill out the edges because we know what the edges look like. This is reject and not reject. This is HO is true, or correct, rather. HO is not correct. Who just came back? Somebody just came back. Alexa came back. All right, we'll start with the boxes where we had happy faces before. So the lower left, I fail to reject, and HO is correct. What happens there? What is the truth of the situation? Not pregnant. Good. I'm not pregnant. The test says I'm not pregnant. Everything is in agreement. We are happy campers. The other happy face box is the upper right. Are pregnant. Yeah. The test said I'm pregnant. I am actually in reality physiologically pregnant. We have agreement. Happy face. Now we have to consider the frowny face boxes. So, upper left, reject the null, but the null is correct. What has happened? A false positive. Remember that the null is I'm not pregnant, so I'm rejecting the statement I'm not pregnant. So I think I'm pregnant. I can write. Come on. I think I'm pregnant, but actually not. I rejected the null, so I think I'm pregnant, but in actuality, the null is correct and I'm not pregnant. That is a false positive. The test said I am, but I'm actually not. As a HO is the, so remember that this is the assumption I'm not pregnant. In reality, this is am pregnant. This is a positive test result. This is a negative test result. Before we fill in the empty box, practice thinking about real-world consequences. The test has told me that I am pregnant. In reality, I'm not. As a person who suspects I'm pregnant, what am I going to go home and do? Possibly cry. But as an adult who's out of like college and financially secure, what am I going to do? You start announcing it. Yeah, what else? Yeah, start planning doctor visits. What else? Yeah, start planning baby showers and invites. Start spending money, right? Buying baby clothes, decorating a nursery. I may change my diet and my habits, right? This is a major disruption in an adult life, right? And all of that for a false positive. So yeah, that would be frowny face, right? There is actual material loss happening in the real world when you get a false positive. Good. Second box that's empty, that's the frowny face box. False negative. The question is, what does a false negative mean? Good. So I think not Craig, but actually am. So actually, I am pregnant. But I walk out of that doctor's office with a negative test result. If I am an adult out of college, a functioning over 21 adult, what could happen? You could injure the baby in a whole lot of ways. Drinking, smoking, like heavy duty exercise, right? Riding on roller coasters that you shouldn't be riding on. There's a whole lot of things you can do that can injure the baby or your body when you're pregnant and you don't know you are. As somebody who has major health problems because their mommy smoked, I can tell you that's not a good thing. The 70s were fun. So again, real world material loss when there's a boo-boo, yeah? Good. Shh. Bring it back together. Shh. So one of the possible FRQ questions is they are going to ask you to do that. Identify what's going on in words, what does that test result mean, and what are the consequences of making that mistake? What are the consequences of that statistical error? This is one of those instances where it's more important that you can justify your response than it is that you have the same response the reader does. This is the part of the test that's BS. As long as you can back it up, you're fine. And some of you are very good at that. I'm very good at that. There's nothing wrong with that. That is a useful adult skill. All right. Summaries about errors in power. Reminders. Type 1 error. I am rejecting the null when I shouldn't. Reject HO when I should not. The null is true. The probability that I make that boo-boo is our significance level, alpha. That's supposed to be an alpha. It's not a very pretty alpha. I'm sorry. It's supposed to look like a Jesus fish. It's hard to write on a TV and talk at the same time. Give me a break. Does that meet with your approval, Your Highness? Type 2 error. I fail to reject the null incorrectly. Meaning I should have rejected and I didn't. Frowny face. The probability of committing that error is called beta, the next letter in the Greek alphabet, because again, statisticians are not terribly creative with naming. It's a curly B. We will not, in this class, cover how to discuss beta or how to calculate beta. We will not discuss how to calculate. I can talk. If you are going to like major in stats or go to grad school in stats, you will learn that eventually. But for most of you, you're going to have a calculator or a computer program that's going to spit this information out at you, and you just need to know how to interpret what the calculator tells you. So beta is the probability that I am failing to reject incorrectly. The power of the test is rejecting correctly. In other words, this is the probability of avoiding a type 2 error. And we calculate it, since it is the complement of this guy, as 1 minus beta. Since we can't calculate beta, we can't calculate power. What we want to do is think about the relationship between those three quantities. And we'll start with beta and power. Type 2 error and power. Because power is 1 minus beta. As beta, probability, a number between 0 and 1, gets bigger, what happens to my power? Goes down. Because collectively, those two numbers have to add to 1. As one gets bigger, the other gets smaller to compensate, so they add to 1. So these guys move in opposite directions. Type 1 and type 2. The probability that I reject incorrectly versus fail to reject incorrectly. Guesses on which way those move. Same direction or opposite direction? Opposite, yeah. Because they're measuring opposite things. One's rejecting incorrectly, the other one's failing to reject incorrectly. I expect these are also going to move in opposite directions. And now a deep question for you. We know that power and type 2 error, opposite directions. We know type 1 and type 2 error are in opposite directions. Guesses about the relationship between type 1 and power? Same direction. Yeah, same direction. Good. So let's summarize. Type 1 and type 2, alpha and beta, have an inverse relationship, opposite directions, sometimes called indirect. As the probability of one increases, the probability of the other good decreases. Opposite directions. Again, the probability of committing a type 1 error is our alpha. It's set with our significance level. As a statistician, that is something I have control over. I choose my significance level at the start of a test. I have direct control over what the probability of committing a type 1 error is. The others will then fall in line with that choice. So if I want to change beta or power, the fastest way to do that is make a change to alpha, because that's the thing I have control over. The higher our significance level, the lower the probability. I know how to spell. Why am I having a brain fart? Don't judge me. Oh my gosh, thank you. That is one of many problems with that sentence, and I have to look at what I wrote there because my poor little brain, for some reason, just all of a sudden blanked right now. I know. It'll be on video forever. You feel free to laugh at me as much as you want. Yeah, when I yeeted the calculator, that's also on video forever. Feel free to laugh. Probability of failing to reject it. You try and stand at a TV and write for an hour in front of a peanut gallery that laughs at you every time you do something silly. It's okay. You can laugh at me. I know I'm silly. Higher our significance level, the lower the probability of failing to reject. because the higher the probability that we are rejecting. So the lower the probability we're going to fail to reject. That is Stewie. That's lovely. I'm glad we're I'm glad we're making good use of our extra space in our notes. Next one, higher significance level, the more likely we will be to reject the null. Because remember that alpha is the probability that I am landing in that tail. My sample ends up in that tail and I reject. So the bigger my tail, the more likely I am to reject the null, which means the more likely I am to do that incorrectly. Last one, type 1 error and power have a direct relationship, which means as alpha gets bigger, what happens to the power? Bigger, yeah, it also increases. Direct means same direction. So as we set our alpha to be a bigger number, 0.1 instead of 0.05, we increase the power of our test. So, as a statistician, sometimes rejecting incorrectly is the worst decision. Sometimes failing to reject incorrectly is a worse decision. As statisticians, they are counting being able to identify what those errors look like in reality and their logical consequences as a key skill. Because I need, as a statistician, to determine which of those outcomes is going to be worse for the situation or scenario. Okay, last example. Deep breath, last example. That was so dramatic. All right, drug manufacturer claims less than 10% of patients who take its new drug for treating gestational diabetes will experience nausea. To test this claim, researchers conduct an experiment at the 5% significance level. What are the null and alternative hypotheses? I heard percent, so 10%, 10%. It's a claim about percent, so what population parameter? Proportion, P. Anytime it's a percent, very good. Null is always a statement of equality. Less, very good. They use the word less than 10% in the description of the problem. Good, good. Perfect, that's it. That's it. Answer the question, check. Next step says describe a type 1 error and a type 2 error in this setting and explain the consequences of each. So type 1, type 2. And remember that type 1, I am rejecting HO incorrectly. And this one I am failing to reject incorrectly. You don't have to jot that down on test day. I'm putting that there as a mental reminder because I forget things while I'm writing. So, first question is, what, as a statistician, am I saying if I reject the null? And the answer is, if I reject the null, I'm supporting the alternative, which says it's less than. So I say proportion of nausea cases is less than 10% when it's actually more than, equal to or more than 10%. It's the other direction. I say it's less than, it's actually the other way. Question. If I am the drug manufacturer and the firm I've hired to run this test has said that less than 10% of patients will experience nausea, when in fact 10% or more are going to experience nausea, what is going to happen to me as a drug manufacturer? What am I opening myself up to? Lawsuits. Yeah, America is a lawsuit happy nation. If all of a sudden there's twice as many cases of nausea as I was expecting as the drug manufacturer, I am opening myself up to lawsuits. Yeah. Right? Lots of complaints. Anything else? What happens to the reputation of that drug manufacturer? Yeah, reputation, loss of face, yeah. Which means lower revenue, which means a whole lot of other bad things for that drug manufacturer, right? Making a boo-boo like that is bad. The question is it worse than the alternative? We have to compare both. All right, next, type 2 error. So I fail to reject when I should, and fail to reject means I'm accepting the null. So I say the proportion of nausea cases is greater than or equal to 10% when it's actually less. So I am a drug manufacturer. I have produced this new drug, and my consulting statisticians have done samples on tests, or tests of samples, and have told me that 10% or more of patients are going to experience nausea as a side effect. As the drug manufacturer, what am I likely to do? My drug is causing more side effects than I would like. What am I going to do? Yeah, take it back to the lab. Let's do some more R&D. Yeah. Which is both time and money, right, for the company. I'm losing both time and money. That's time the drug could have been on the market where I'm making profit. That's money I'm spending on R&D. And the question as the medical researcher and their statistician team is which one of those is likely worse in the long run? And out of curiosity, what do we think? So if you think it's type 1 error is worse, give me a thumbs up. If you think type 2 error is worse, give me a thumbs down. I see a lot more ones. I see a couple of shakies, but mostly ones. And I think I agree, because long term, a loss of rep and lawsuits, that's going to affect my profit over decades. Whereas this is a much shorter time frame where I'm losing income. Yeah. And it's never going to hurt me to produce a medication that causes fewer than the assumed amount of side effects, right? It's always better to have fewer side effects on meds. So more R&D generally doesn't hurt in the long run. Good. Very good. 2 more questions about power. So it says the test we performed as the consulting statisticians has a power of 0.54 to detect that the alternative is supported. Correctly reject the null. Explain what the power means in this setting. What is one way we can increase the power? So we're going to start with what the power means. So we go back to when we first learned about power, and we know that it's the probability that we correctly reject the null. So there is a 0.54% chance we correctly reject that the proportion is equal to 10% and support the claim that it is less than. That's what power is measuring. What is the chance that I correctly reject the null? So that's just using the definition of what power is. The second question is, how do I increase it? Bless you. And what's the one way that we as statisticians have control over power? So I go back, and we go here. Type 1 error and power have a direct relationship. As type 1 error increases, power increases. If I want to increase power, what do I increase? Type 1 error, which is my alpha, my level of significance, which is the only thing I have control over. I don't have direct control over type 2 error percentage. I don't have direct control over power, but I do have control over my significance level, alpha. Yeah. Oops. Last question. You know the power of the test at the 5% significance level is 0.54. If we decide to use alpha is 0.01 instead of 5%, no other changes to the test. Does the power increase or decrease? How do we know? So I'm going to give you just a second to contemplate, and then you're going to show me on your thumbs. If alpha goes from 5% to 0.01, does power go up or down? We got it in our heads? All right, I want to see thumbs. In 3, 2, 1. Show me your thumbs. And I see mostly thumbs down popping up. Good. Alpha went down. Power should go down because alpha and power go in the same direction. Good. Marissa, would you do me a favor and approve the pass? Thank you. That does not get me enough credit because they asked explain. So first explanation is I know power and alpha have a direct relationship. More specifically, alpha is measuring just the percentage that I reject. And if I decrease the percentage that I'm going to reject the null, I'm also decreasing the percentage that I'm going to reject it correctly. I slept funny and like this whole part of my body just hurts. I don't know what happened last night. Got punched in the face? Oh, I'm sorry. Yeah. I'm glad I am in math where we don't usually throw fists. That's not for me. Good. Questions on that example? No, big ideas, yeah? We're going to practice with them again and again because, like I said, we're going to do multiple significance tests throughout semester 2. You're going to have lots of time to process. Make sure you're spending time on your homework. I have a question for you. Show of hands, how many of you have an active study group where you meet to study for stats or do homework together? That is way less than half the class. That is concerning this close to AP test day. My second master's, I studied how human brains learn math and science. That was what I was working towards a PhD in. And I am telling you that you meeting with friends and talking about the math will help you retain it better than anything I do for you in class. You have to be meeting with your friends and talking about the math. So if you don't already have a homework group, build one. My room is open after school. My room is open at lunch. The library is open after school. The library is open in the morning, right? There's lots of places to study. I have an open door policy. Anytime that thing is propped open, you are more than welcome to come in with your friends, claim a table, and chill. Yeah? And if people are in here, I'm more likely to stay late. I leave early when nobody shows up. I'm willing to stay till 5:30 if you need a place to stay. Yeah? Okay. Last chance for questions on the notes before we move on. Yes?
I just want to make sure. So on the test, are there going to be questions that are asking like which type of error is like worse? Because like on here it said like which.
Gotcha. So generally no. If a question like that pops up on the FRQ, they're going to ask you to describe what the error looks like in context and then describe the consequences of it. They don't typically ask you to make a value judgment on which one you think is worse. No. That was a good question. Other questions? No. All right, you need to clear your desk of everything except a calculator, something to write with, and your notes. And one person from your table needs to go grab a couple books off the bookshelf. We're going to do our Unit 6, Part 1 Frappy.